Good afternoon, ladies and gentlemen. This course is designed for people who want to master SQL at the middle and senior levels. We will discuss the Oracle database as an example, but all the working and research methods can be applied to other relational databases. In our course, we will talk about such an important aspect as query optimization and will deeper analyze the theoretical questions that may be useful not only for successful work, but also for the interviews. What you should already be able to do: write basic SQL queries, use aggregate functions, use analytical functions, and write your own functions. In PostgreSQL, or speaking of Oracle, using the with construction, a new feature introduced by Oracle, and according to the presentation, it should work 4 times faster than PostgreSQL variant. Query plan. Consider a simple situation where there is a query that loads the database very heavily and needs to be optimized. Or let's pretend there is an urgent need to complete it very quickly because management expects a quick result from us. The first thing that needs to be done before executing is addressing the query plan. The query plan is a sequence of operations that the DBMS will do to get the result of the written SQL query. Skill set, we can see how Oracle or any other DBMS executes these queries under the hood. There are 2 types of query plan: a potential explain plan and an actual execution. Why are there 2? For an analogy, imagine a taxi ride. Time and route shows you it's an explain plan for the current state of the roads. But at the moment you start your route, there are a lot of factors that you could not predict: accidents, all kinds of emergencies, and unscheduled work. This means that in order to shorten your path and avoid an increase in travel time, your taxi driver will change the path. And this is the difference between execution and explain plans. In the DBMS, everything happens in a similar way. However, if your system is well designed and the load is optimal, then the occurrence of an emergency is minimal, which means there will be almost no difference between explain and execution. Therefore, in practice, they are almost the same. Let's figure out how to see explain plan. The first and the easiest way is to do it in your IDE like PostgreSQL Developer, Oracle SQL Developer, the Beaver, and others. Usually a hotkey is used. It's either F8 or F10 or the web interface. A universal way is to do this using the DBMS, for example, using the construction below. What do we see? Query execution order using data structures, join algorithms that are used to join tables, the indexes it applies if they were pre-built for those tables, performed operations, sorting, aggregation, and other. It is worth noting that DBMS is kind of smart. It means it has a query optimizer at its disposal. This is a tool that can go through all sorts of ways to get the result that you specified in the SQL query and leave the most optimal one. Therefore, the query plan might differ somewhat from what was written by you, since the DBMS considered it to be suboptimal in this case. There are also many ways to get an execution plan. The simplest one is, as mentioned in the slide. Or you can look at this. How to read a query plan. Consider the explain plan that we got based on our query from the paragraph above. Let's see what the fields in our table are: ID, parent ID, operation, options, object name, object type, cost, and bytes. To make the query plan easier to read, it is presented graphically. It is a tree looking like this. Even for a person who has never read it, but is familiar with the terms, it will be easy to find useful information in it. For example, let's pay attention to the sales product ID index, which appears in the plan. Nested loops, hash join algorithms can be seen there. First glance at the keywords can mislead to the consideration that the index is working, but in fact, this assumption may be wrong. So let's figure it out. To begin with, it is important to know that all operations are linked by the parent-child relationship and are reflected in the corresponding fields of the parent ID and ID table, or in the form of individual branches of the tree in the picture. DBMS uses the depth-first technique when executing the plan. This means that the DBMS first accesses a node with 0 depth, and then moves down to the very last child. In our example, its depth is 5, which is the lowest value in the tree. You can trace this order by the ID and parent ID fields in the table. And then the DBMS begins to sequentially perform operations, moving to the top. The conditional graph, the order drawn by the arrows, will look like this. Now let's go through the steps in consequent order. Start at the top of the plan again. Select the operator depth equals 0 and go down to the first leaf. This is an access to a table with a full table of products depth equals 5. And we pass the data top to ID equals 4. Statistics collector ID equals 4 buffers rows from the first step of the execution plan. After the optimizer selects a subplan, buffering is disabled and the statistics collector stops collecting rows and skips them instead. On subsequent executions of the same SQL query, the optimizer stops buffering and chooses the same plan instead. Since Oracle 12, such a feature as an adaptive query plan has appeared, which is determined in time based on the number of rows. In our case, it can be either hash join ID equals 1 or nested loop ID equals 2. Either the number of rows will be small, then nested loop will work faster, or we get so many rows that we need to use hash join. Let's consider nested loop variant. From the sales product ID index, using the range scan method, row ID rows are determined and passed to the top at ID equals 3. Nested loop ID equals 2 combines two sets of full table products and row ID rows from the index. The result set is merged with the sales table in step ID equals 7 by row ID. The final set is passed to the select statement ID equals 0. Let's look at alternative plan with hash join. The statistics collector ID equals 4 captured rows from products above the threshold and passed them to step hash join ID equals 1. In hash join, sets of rows from ID equals 5 and ID equals 8 are combined. The final set is passed to the select statement ID equals 0. So let's see what the optimizer chose in the end. We see that the steps in ID in 1, 4, 8 were ignored, and the final query plan went through the nested loop connection. If there were the bias, then the plan would look like this. There are mainly 3 join algorithms: nested loop, hash join, and sort merge join. The connection type can be found in the operation field in the query plan. The optimizer determines which of these algorithms to apply to a particular join in the process of building a query execution plan, since, depending on the conditions, each of these algorithms can be more efficient than the others. In other words, in some conditions, nested loops will be more effective, and in some, merge or hash match. Nested loop is the simplest of them and has linear complexity. Imagine we have 2 tables, a small table that contains products. We suppose there are not very many products in our store, and a huge table that contains the sales of all products. we need to join these two tables. In this case, nested loop will be used as the join algorithm. How exactly will it work? The algorithm will go through each row in the sales table and compare against each row in the products table. Skill said, in the worst case, we'll run n times n times, where m and n are the number of rows in the tables that we are joining. Interpreting the algorithm in any programming language, for example in Python, it will be implemented using two loops. Thus, we have two loops, external and internal, hence resulting the name nested loops. You can optimize the nested loop algorithm by building indexes on the table join keys. Hash join. The hash join algorithm proceeds in two stages. A hash table is built in the first step by calculating a hash value for each row of one dataset, usually the smaller of the two. These hashes are computed based on the join keys of the input data and then stored along with the row in a hash table. In the second step, a hash value is calculated and a hash table is searched for matches for each row of another dataset using the same hash function. If it finds a match for that hash, then it checks if the join keys between the row in the hash table and the row in the second table really match. It needs to do this check due to potential hash collisions. Hash collision is an instance when a computed hash from two different rows produces the same hash. Hash join works well in both large and small tables. It works faster than a nested loop, but loses in those cases when the operations for collecting hash map tables take longer than just running through the table. The hash join method is highly recommended when the large, unsorted, and non-indexed datasets are processed, because of its high efficiency in this case. Sort merge join. This type of physical data join is the fastest and most efficient in cases of two large datasets. However, it requires them to be sorted, for example, indexes of the join columns. The principle of operation of this join type is as follows. The server receives the first rows from each set of input data and compares them. Then it continues comparing the next rows from the second set until the values match the values from the first dataset. As soon as the values do not match anymore, the server moves to the next row in the set with a lower value and continues to perform comparisons. This process is repeated until all rows have been processed. This algorithm is efficient because we don't have to return and read any line several times using it. That is, data reading occurs only once. However, the algorithm becomes less efficient when there are duplicate values in the sets. That is, when a many-to-many merge join occurs. In such cases, SQL Server writes any duplicate values from the second table to a temporary table and performs comparisons there. Then, if these values are also duplicated in the first table, SQL Server compares them to the values already stored in the temporary table. The nested loop is preferable when one of the tables is very small, and it is faster to run through it than to sort these tables or build a hash table, because sorting and hashing are rather expensive operations. If the tables are quite large enough and our join condition is based on strict equality, then the hash join would be a decent choice. But if either the join condition in the query is different from the strict equality, or there is not enough memory to build hash tables, or if the tables are sorted, then the sort merge join would be a great option. In general terms, an index in databases is a file with a sequence of pairs of keys and pointers. An index is used to speed up the search through the database. It allows you to find a row with a specific column value while looking through only a small part of the total number of table rows. Poorly designed indexes and insufficient numbers of them are a major source of bottlenecks in database applications. Their efficient design is of paramount importance for achieving high performance. Accordingly, it is better to build an index for those fields on which we are joining tables or selecting values with the where operator so that the value can be found faster. Indexes are not needed when, first, in case of a small tables, since it will be faster to read the entire table and store it in memory. And secondly, in tables with massive data update or insert, since in this case, the recalculation of indexes will be constantly initiated while data insertion, which will significantly affect overall performance. If there is a need to index such a table, nevertheless, then it is recommended to delete the indexes before the data insert and rebuild them after. There are several types of indexes. First, B-tree. The B-tree family of indexes is the most commonly used index type, organized as a balanced tree, indicated by the letter B, balanced, with ordered keys in it. They are also supported by almost all DBMSs, both relational and non-relational, and for almost all data types. Oracle has its own B-tree. These are regular indexes created by default when you use the create index statement. B-tree indexes are structured in the form of a reverse tree, where top-level blocks are called branch blocks and lower level blocks are called leaf blocks. In a node hierarchy, all nodes other than the top one or root node have a parent node and may have 0 or more child nodes. If the depth of the tree structure, that is the number of levels, is the same from each leaf block to the root node, then such a tree is called balanced or B-tree. B-trees automatically maintain the required index level for the size of the table. B-trees also ensure that index blocks are always at least half full and less than 100% full. B-trees allow select, insert, and delete operations with very few insert-output operations per statement. Most B-trees have only 3 or fewer levels. You only need to read blocks of the B-tree when using it, so the number of insert outputs will be limited to the number of levels of the B-tree. Let's say 3. Plus 2 inserts outputs to perform an update or delete, 1 for reading and 1 for writing. And it only takes 3 or fewer disk accesses to perform a B-tree search. Oracle's B-tree implementation always keeps the tree balanced. Leaf boxes contain 2 elements each, the index column values and the corresponding row ID for the row that contains the column value. Row ID is an Oracle unique identifier that identifies the physical location of a row and provides the fastest way to access a row in an Oracle database. An index scan quickly yields the row ID of the row, and from here it can be quickly accessed directly. If the query only needs the value of the indexed column, then of course the last step is omitted, since there is no need to retrieve additional data other than what is read from the index. This type of index is optimal for a set with a good distribution of values and high cardinality. Number of unique values. Number 2, bitmap index. The bit index or bitmap method is about creating separate bitmaps, sequences of zeros and ones, for each possible column value, where each bit corresponds to a row with an index value, and its value equal to 1 means that the record corresponding to the bit position contains an index value for this column or properties. Number 3, reverse index. This is also a B-tree index, but with a reverse key. Reverse indexes or indexes with reverse keys are almost the same as simple indexes, except that when indexing data, the order of viewing this index is reversed. For example, in case of a table of exchange rates, it is effective to read it from the end because we often refer to exchange rates over the past few days. Number 4, inverted index. An inverted index is a full text index that stores for each key token a sorted list of the addresses of the table entries that contain the given key. Number 5, spatial indexes. For spatial data types, there are spatial indexing methods based on R-tree index, and grids, in sense of grid-based spatial index. Oracle supports spatial indexes, R-trees with quadratic partitioning, and quadtree. Quadtree is a subtype of the grid-based spatial index, in which there are always 4 children in the parent cell, and the grid resolution varies depending on the nature of complexity of the data. R-tree, radius tree, is also a tree data structure proposed in 1984 by Anthony Gutmann. This data structure also splits the space into many hierarchically nested cells, which don't have to completely cover the parent cell and may overlap. Various algorithms can be used to split overflowing vertices, which leads to the division of R-trees into subtypes, with quadratic and linear complexity. The quadratic subtype is about splitting the space into 2 rectangles with a minimum area covering all objects. Number 6, functional. Number 6, function-based index. The most flexible index type is the method of functional indexes, the indexes whose keys store the result of user-defined functions. Functional indexes are often built on fields whose values are pre-processed before being compared in an SQL command. For example, when comparing raw data in a case-insensitive manner, the upper function is often used. Creating a functional index with the upper function improves the efficiency of such comparisons. In addition, a functional index can help to implement any other method type of indexes in a given DBMS, except perhaps a bit index. For instance, hash for Oracle. Hint is a tool that allows us to influence the query path. It is worth remembering that a hint is not a rule, so it does not guarantee that the query planner will use them. The query planner may ignore your hint if it considers it suboptimal or if you made a syntax error. If all possible options for executing an SQL query are represented in the form of a graph, then it becomes obvious that going through the whole query is excessive due to the long execution time. Accordingly, hints help us cut off certain branches and take into account others. The increase of the query's costs in the query plan is quite possible because of the use of the hints. The standard syntax for calling hints looks like this. The space after the plus sign is important. Don't ignore it. It's a common mistake. There is a select example down below where the number of hints can be from 1 to n. So how it works? Let us imagine a situation where there is data in tables that we somehow process. This is the corresponding data input block. We have written an SQL query that converts it into a data output block. The optimizer looks for all possible ways how this can be achieved by various operations. But since a complete enumeration and evaluation of all possible paths is a labor-intensive operation, only a part of them is evaluated. The corresponding paths are highlighted in white. The cost of each path is estimated and the most optimal one is chosen. The optimizer may be forced to take into account For example, the connection algorithm we are interested in if the hint is used. After that, the cost will be evaluated once again by the optimizer and the optimal one will be chosen. As we see in our example, the original one has been chosen. That is why this is a hint, not a rule. But hints allow path not only to be taken into account, but also to be excluded. This is necessary, for example, to remove paths that lead to any bugs. Then the optimizer will not take it into account and choose another path. So, where are hints are useful? When the optimizer chooses the wrong query path, basically. Usually the reasons are as follows. First, bad or outdated statistics. 2, complex query with a branch of connections. 3, bugs, for example, when using data structures such as JSON, XML in a query. Number 4, the limitations of the query optimizer to see all the options. And the last, when it's necessary to take advantage of additional query manipulation features, such as result caching, cursors, parallel execution, direct path insert, and others. When should hints not be used? First of all, for scheduled queries, it should be understood that the system is dynamic and changes over time. And where a nested loop used to be more effective, in a couple of years, this may not be the case. Secondly, low level of specialists. The problem may seem far-fetched, but there are many companies that recruit students to support routine requests. And code with hints is more difficult to them to maintain. Sometimes this leads to a disastrous results. The third one, main optimization. Hint optimization is used when there are no other alternatives. Since any problem can be solved usually by eliminating the original problem, for example, by creating indexes or by means of collected statistics, there is no need to degrade to using a top-level crush, except an ad hoc in case of a limited time scenario. Okay, hints may affect on optimizers modes, the order of access to tables in the from block, choice of join algorithm, combination of indexes, execution methods of the subqueries, manipulating statistics, transformation of subqueries, manipulating cursors, using parallel execution, caching, and manipulating the recording method. In Oracle database, the optimizer plays a major role in executing SQL query in the most efficient way. To develop the best execution plan for any SQL queries, the optimizer first evaluates possible access paths, join orders, etc., and selects a number of suitable execution plans. It then calculates the cost of alternative plans based on insert outputs, CPU, and memory usage. At this stage, the optimizer uses statistics, which include information about the distribution of data and the storage characteristics of tables and indexes. Finally, the optimizer compares the costs of the alternative plans and selects the plan with the lowest cost. The statistics collected include table or index size in database blocks, number of rows, average row size, and number of chains. It's only for tables. Height and number of leaf rows removed. This is only for indexes. This information may change when data is inserted, deleted, or updated. Since maintaining real-time data distribution statistics is detrimental to performance, these statistics are updated from time to time when statistics are collected on tables and indexes. With the DBMS stats package, manual collection of optimizer statistics at the table, schema, or database level and system statistics is available. However, starting with Oracle Database 10G, The recommended way to collect statistics is to let the database do it automatically. Nevertheless, it is necessary to use the traditional DBMS test package to collect statistics instead of relying on Oracle's automatic collection in some situations, such as those we will describe below. First, it's the use of external tables, collection of system statistics, collection of statistics about fixed objects, such as dynamic performance tables. And immediately after inserting a large amount of data, as it renders the available statistics out of the data. To check the statistics of tables in a particular schema, use the following query. You can see it on screen right now. And to check index statistics, use the following down below. Partitioning. One of the effective ways to improve database performance is partitioning of tables and indexes. Further, I mentioned different partition methods and their features. In general, partitioning is generally understood not as some kind of technology, but rather as an approach to database design, which appeared long before DBMS began to support the so-called partition tables. The idea is very simple: to divide the table into several parts of a smaller size. There are two types, horizontal and vertical partitioning. Let's take a look at the first one, horizontal. Parts of the table contain its different rows. Suppose we have a sales table of some abstract application, sales. We can split it into parts, one for January 2021 logs, one for February 2021, and so on. Let's address the second one, vertical. Parts of the table contain its different columns. Finding a use for vertical partitioning when it is really justified is somewhat more difficult than for horizontal partitioning. Oracle has supported partitioning since version 8. Partitions can be deleted, divided, transferred, and divided into subpartitions. Various options for indexing a partition table are supported, with global index, partitioned index, and so on. Oracle uses various types of partitioning for tables. These are some of them. Partitioning by ranges of keys, range partitioning. Related table data, where the values in the given columns belong to a certain range, are distributed over the corresponding fragments or partitions of the table. Our example with sales table is right about that. Partitioning by the list of key values, or list partitioning. You specify a discrete set of values that defines the data to be stored together. For example, you can specify that rows with a value in a column that is in the list AB go to partition 1. Rows with a value from the list CDF go to partition 2, and etc. Hash partitioning. A hash function is applied to the column or columns, and the row will be placed in the partition according to the value returned by this hash function. Let's use client ID as partitioning key. It should be noticed that the distribution of values for this column may be irregular. Partitioning by key intervals, or interval partitioning. It is very similar to key range partitioning, but with the difference that the database itself can create new partitions as data arrives. With traditional key range partitioning, the database administrator must pre-create partitions to hold each possible data value both now and in the future. This usually means that the DBA creates partitions on a schedule, preparing them for data storage for the next month or next weeks. With key range partitioning, the database will automatically create partitions when there is new data that does not fit into the existing partitions, based on a rule specified by the database administrator. Reference partitioning. This one allows a child table within a parent-child relationship provided by a foreign key to inherit the partitioning scheme of the parent table. Previously, a table could only be partitioned based on physically stored attributes. Partitioning by key intervals and references, or interval reference partitioning. As the name suggests, this is a combination of key range partitioning and reference partitioning. This type of partitioning is available starting with Oracle 12c. It makes it possible to automatically add partitions to parent and child tables, partitioned by reference. Partitioning by virtual column or virtual column partitioning. This one allows you to partition by an expression based on one or more existing table columns. The expression is only stored as metadata. And the last one, composite partitioning. It is a combination of range partitioning, hash partitioning, and list partitioning. It allows you to first apply one partitioning scheme to some data, and then split each resulting partition further. For example, the composite range hash partitioning, where the table is divided into partitions by range, partitions are divided into subpartitions by hash. Index partitioning. Indexes, like tables, can be partitioned. There are two methods available for this. The first one, equipartition of an index with a table, also known as a local index. For each table partition, an index partition is created that indexes only that table partition. All entries in a single index partition point to a single table partition, and all rows in a single table partition are represented in a single index partition. Partitioning an index by a range or hash value, also called a globally partitioned index, is the second one. Here, the index is partitioned by range or optionally by hash value in Oracle 10G and later. And a single index partition can point to any and all at the same time partitions of the table. This slide demonstrates the difference between local and global indexes. Note that in the case of a globally partitioned index, the number of index partitions may differ from the number of table partitions. Local indexes should be used if there is a need of an index with list or composite partitioning, because global indexes can only be partitioned by range or hash value. The local index will be partitioned in the same way as this table it belongs to. Let's look at example number 1. Let's create a local partitioned index on the sales table. The partition key for this table is the sales date as date column. The index creation code snippet is shown below. Note that the example did not use the partition by range clause when creating the index. Oracle automatically takes the partition structure for the index from the partition structure of the underlying sales table. You can also omit clauses like partition STIQ02 tablespace TS02. If partition is omitted, then Oracle will automatically create the partition names. If tablespace is omitted, the Oracle will automatically place the partitions in the same table spaces as the corresponding partitions in the base table. Let's switch to example number 2. A globally partitioned index has a partition structure that is different from the partition structure of the index's base table. As an example, let's create a globally partitioned index on the sales table. Let's take the column custom ID as custom ID as the partition key for the index. The code snippet below uses other index spaces names TSI01, TSI02, TSI03 for index partitions. The number of index partitions doesn't match the number of base table partitions for this index. Local indexes have certain properties that make them the best choice for most data warehouse implementations. Local indexes are more flexible when it comes to partition maintenance operations. If the DBA decides to move a table partition, only the associated local index partition will require rebuilding or maintenance. In the case of global index, all index partitions must be rebuilt or maintained in real time. In some cases, Oracle can take advantage of the fact that the index is locally partitioned on the table and develop optimized query plans based on this. There is no such relationship between the index partition and the table partition in the case of global indexes. Local indexes also make it easier to restore partitions to a point in time. If for some reason a single partition needs to be restored to an earlier point in time, then the rest of the table of locally partitioned indexes can be restored to the same point in time. All global indexes for this object will need to be rebuilt. This does not mean that global indexes should be avoided. In fact, they are vital for performance reasons. You just need to be aware of the implications of using them. Caching. Caching is the process of storing data in memory. The prerequisites for this is that the speed of reading from memory is higher than from a hard disk. And secondly, is that there is no need to recalculate the written result of previous calculations. This technique is also called memoization. Result cache. Suggesting there is a query in our database that runs very frequently, like over 10 million calls per month. Then result cache comes in handy. The result cache stores the results of SQL queries and SQL functions in a new SGA component called result cache memory. It works like this. The first time a query is executed, the database caches its results, and on subsequent calls, it simply retrieves the result of the query, rather than calculating it again and again. If any of the objects that are part of a query change, the database will invalidate the cached results of that query, but we will always get back the actual result. The result cache consists of two components, the SQL query result cache, which stores the results of SQL queries, and the PL/SQL function result cache, which stores the values returned by PL/SQL functions. Whether the database caches the query result or not depends on the value of the result cache mode in initialization parameter, which can take two values, manual or force. The slide provides a brief description of how these two values affect results caching behavior in the database. In case of force parameter, the database will try to cache all results wherever it can. The cache step, however, can then be skipped by including the no result cache hint in the query. In case of manual parameter, the database will cache query results only if the query has a result cache hint. The SQL result cache can be used in subqueries. The SQL result cache is a new cache in the SGA, similar to the buffer cache or program global area. The cache size is determined by several initialization parameters. There are several data dictionary reviews that shows SQL result cache statistics. The SQL result cache allows you to cache the results of queries that access a large amount of data. When the main table changes, the cache is automatically invalidated without your intervention or writing any additional code. Since the amount of memory is limited, you should put queries in them that return a small amount of data about a few lines long. If the cache space is full, then the new query will clean up the older results and write down its own result. PL/SQL function result cache. Let's talk about it. Starting with Oracle Database 11G, it became possible to cache the result of PL/SQL functions. Enabling function result caching for a specific function provides the following benefits. Oracle stores inputs and their corresponding return values in a separate cache for each function. The cache is shared by all sessions connected to the database instance. It is not duplicated for each session. In Oracle Database 11G Release 2, and later, the function result cache is even shared between instances in the real application cluster, or RAC for shortening. Each time this function is called, the database checks if the result was cached with the same input values. If there is a cached result, the function is not executed. Instead, Oracle simply returns the stored value. Whenever changes are committed to tables identified as dependencies for cached data, the database automatically invalidates the cache. On subsequent calls to the function, the cache is refilled with consistent data. Caching occurs on every function call. It does not need to be specifically enabled for SQL commands. No need to write code for declaring and populating collections. Instead, caching is enabled using declarative syntax in the function header. Result caching is most commonly used for functions that query data from tables. Good candidates for result caching are static datasets such as materialized views. The content of these views doesn't change between updates, so why fetch the data again? And the second one are tables that are queried much more than the rate of change. If a table changes on average every 5 minutes, but the same rows are queried hundreds or thousands of times between changes, the result cache can be put to good use. But if the table changes every second, caching the results is undesirable. It can only slow down the application, since Oracle will spend too much time filling and then clearing the cache. Choose carefully when and how to use this opportunity. Talk to your DBA and make sure that the result cache CGA pool is large enough to hold all the data cached under typical load. So let's consider an example of use. The relies on construct indicates that cache depends on the partners table, and if it changes, the cache should also not be used. The relies on construct is optional, and as of Oracle Database 11G Release 2, it is no longer needed. Starting with this version, Oracle automatically detects which tables the return data depends on and correctly invalidates the contents of the cache when the contents of those tables change. Including your relies on section will do nothing. The database will perform functions again only if the following cases. First, bypassing the result cache by not specifying the result cache hint. Second, while running the DBMS result cache bypass procedure to force functions and queries to bypass the result cache, regardless of the result cache mode setting or the result cache hint. The third one, if any of the underlying objects of the function have changed and the relies on construct have been specified in the function definition. And the last one, if cached results are deleted by the database because the system needs more memory. Temporary, intermediate tables, and materialized views. Let's start with temporary tables. Oracle allows you to create temporary tables to store data only for the duration of session or even a single transaction. After the end of the session or transaction, the table is cleared. All rows are automatically deleted. Temporary tables are convenient when you are dealing with complex queries or transactions that require storing temporary information before writing it to permanent tables. While Oracle does not parse temporary table data for data distribution, this is not a problem for efficient query processing because temporary tables can store constantly available joins and other information in one convenient location. Instead of running complex queries on permanent tables multiple times, these tables can be accessed multiple times. When the transaction or the session ends, they are truncated, depending on how the temporary table was defined. Temporary tables greatly reduce the amount of redo log activity generated by transactions. Redo logs fill up less quickly when using temporary tables during complex transactions. Temporary tables can be indexed to improve performance. Sessions can update, insert, and delete data in temporary tables just as they able in permanent tables. Data is automatically deleted from the temporary table at the end of a session or transaction. You can define restrictions on temporary tables. Different users can access the same temporary table, each seeing only their own session data. Temporary tables provide efficient data access because complex queries don't have to be run multiple times. Minimum amount of temporary table logs means more efficient query processing. The structure of the table is preserved after deleting the data, which helps to use them in the future. The onCommit preserve rows option in the example you see right now specifies that the table data is saved for the duration of the session, not the duration of the transaction. The onCommit delete rows option clearly indicates that the data in this table should only remain for the duration of the transaction using this temporary table. Let's look at the intermediate tables. As we have already discussed in the caching section, there are queries that are executed constantly, and their results can be stored in the cache to reduce the load and quickly get the result when their volume is small. But when their volume becomes very large and the result is used in many places, and not only within your session, then the technique of saving the results to the hard disk is used, those in the form of a table or a materialized view. Saving to a staging table with a create table and insert into statements is easy for anyone. It is possible to drop a table with a drop table statement and recreate it each time to update the aggregate. Or use truncate delete to clear the table of data that is no longer needed. A procedure is usually created to update an intermediate table, a procedure in which all the logic of filling this table is taken out and a separate job is created, which triggers its execution. If the filling logic is quite simple and fits within the framework of the SQL query, then a materialized view comes to great use, which takes all this work upon itself. Now we will talk about the materialized views. They are similar to normal views in the way that they are a logical view of your data based on a select statement. However, the underlying query result set has been stored in a table. The upside of this is that when a materialized view is requested, a table that can also be indexed is requested. Also, because all connections were resolved at the time the materialized view was updated, the connection cost is paid once, or as often as the materialized view is updated, and not each time you select from the materialized view. Also, with query rewrite enabled, Oracle can optimize a query that fetches from your materialized view source so that it reads from your materialized views instead. In situations where materialized views are created as a form of aggregated tables or as copies of frequently run queries, this can significantly speed up the response time of the application for an end user. However, the downside is that the data obtained from the materialized view is as up to date as it was the last time the materialized view was updated. The syntax for materialized views is quite simple. You can look it by yourself. You need to pay attention to the following keywords in the above sentence. First, the build immediate clause populates the materialized view at the time it is created by default. The alternate clause build deferred only creates a structure. You can populate the materialized view later using the dbms mu package. Use build deferred to populate the materialized view at the end of the business day to avoid impacting normal operations. The refresh clause specifies how Oracle refreshes materialized view data. In the example above, complete updates are the only option. Fast incremental updates are also possible. However, there are a number of limitations and warnings for them. See the Oracle documentation for more details. The refresh clause also specifies when Oracle updates the materialized view data. In this example, the materialized view will be updated on demand because you selected it on demand, only when you explicitly update it using the dbms mu package. If the declared query of a materialized view contains summary measures and key figures of only one table, or if this query joins data from several tables but does not contain any summary measures, then Oracle can automatically update the view when the transaction is committed. You need to use onCommit. Each time, transaction commit for the master tables of the view. The query rewrite option must be enabled in order for the Oracle optimizer to rewrite queries to use materialized views. This option can also be set later using the outer system or outer session SQL commands. The S clause describes the columns and rows of the materialized view using the original SQL query. So, to manually update the data in a materialized view so that it displays the latest information from the detailed tables, you can call the refresh or refresh OM views or refresh dependent procedures of the dbms mu package. The following PL SQL block updates the sales summary materialized view in the sales F scheme.